Hello, hello.
Good morning. Good afternoon. I'm sorry,
Oh,
Professor.
thank you. No problem. Good afternoon, Shawnee. Hello. Good afternoon, Josephine, Claudia, Paulina, Maria. Wait, I'm skipping. I mean to say, good afternoon, Claudia. Good afternoon, Paulina. Good afternoon, Maria. Good afternoon, Mohammed. Good. And there's okay. Oh, and there's the chat. You guys are beating me. I'm gonna keep going with my. Okay, no, I'm not. And we're gonna start in a minute. Let's see. But it's good to see people that I'm seeing. Afternoon, Eric. Hello, Katie. Good afternoon, Alexis. Good afternoon, Shirley. Good afternoon, Emily. Hello, Josephine. Good afternoon, Claudia. Good afternoon, Cheyenne. Shy. Um, Good afternoon, Brandon. Good afternoon, Logan. Good afternoon, Stephanie. Good afternoon, Jada. Good afternoon, Maria. Good afternoon, Mohammed. Good afternoon, Alan. Good afternoon, with two exclamation points, Paulina. Hello, Christina. Okay, I actually think that's everybody. Is that everybody? Okay. Obviously, if I said your name twice, it's because I look at the videos, then I look at the chat, blah, blah, blah. Nobody cares besides me. I'm not even sure I care. Okay. I do care. It's just unclear what I care about. Okay. All right. So let's actually get rolling. I think it's great to see a full group. Okay. Okay. So I'm still catching up I'm still catching up with individual feedback. Believe me, I know that. So we're at a point now where mostly still I owe you points, not the other way around. Again, I'm just going to quickly say, because I know people are so, if you ever get a score that's less than the highest possible score and you don't see any feedback, that means I still owe you more scrutiny and more points. It doesn't mean you got anything wrong necessarily at all. And it definitely means you shouldn't be doing anything. You should just be waiting for more from me. Um, I hope that's getting increasingly clear. I've been getting some emails and texts and stuff. Also, I hope it's increasingly clear that yes, you can still be turning in work. Please, yes. It's a series of drafts back and forth between you. And I'm only repeating that because a couple of people texted me. So I think it's still landing on some people that, yes, it is not too late for you to do anything. And it's not too late for me to give you more feedback and more points. Okay. That said, I do want to dive into physics substance today. I think we had a very productive class. Oh yeah. Okay. So hopefully you got the message that you weren't supposed to do any new sheets for today. You're still trying to catch up now. Wherever you're behind, if you are, you're still trying to catch up. You're not getting any new problem sets for a little while, and I'm catching up with you. But hopefully you did get the message. I'm going to say this quickly because if this is not clear, it needs to be clear. Like last time we had this, we started getting ourselves set for homework 4 sort of by student request, which I think was great. So we like hopped over homework 2. So just want to make, I think this was clear to most of you. It looks clear in the Google Classroom, but I posted, but so then I did the opposite thing in the other class, right? Everybody's clear on this. I think like in the other class, I went heavily over the hard part of homework 2 and made a video of that. So I asked you guys over the weekend to watch the video from the other class. I think most of you did. I didn't ask you to write anything about it. Sometimes I do that, like as a check, but I didn't. So I just want to reinforce, if somehow you didn't get the message or it wasn't clear, it is definitely not too late and it'll help you a lot. It'll be necessary. If you haven't watched the video that was posted in Google Classroom, after the afternoon section of this class from last Wednesday, please do. If you need to text me to make me make that clearer, like give you the exact link or whatever, I'm happy to do that. But please, because I'm not going to go over it again, or not in deep, like I'm not. Like they went over the hard problem of homework 2. I want you to watch that video so I can move on. And if that's unclear at all, please put in the chat. Maybe it's in the chat right now. Something's in the chat. Oh, hello. Hello, Jenna. Okay, awesome. Okay, well, that's clear, right? Just did me electronic. Even if you didn't do it yet, it's clear that that's like what you're supposed to do. Watch. Yes. Okay. Thank you, Maria. Good enough for me. Okay. Now, in that spirit, what I want to do, because also, you know what, I'm doing all this because I really am getting a lot of feedback from you guys in general, which is so helpful. Like, I really am, like during class and outside of class. So, like, a couple of you, were concerned about homework 4, asked me about it in advance. And then a couple of you over the weekend said, can we please go over homework 4 this Monday? I think it's homework. Yeah, average acceleration. Now, just to be, of course, I would have done that at some point, and that is the next plan. I would never leave you just high and dry with the homework like that. But it's true that I might not have done that today. I might have done homework 3 today, but I think since homework 4 is so like on the burner for so many of you, I think it's great. So we're going to get into homework 4 in a moment. I'm then going to say we're still not going to assign any more sheets because there's still catching up and filling in holes to do. So I'm just going to say that we still have to circle back and do homework 3. That will still happen. That's a very much of it's its own thing. So I'm keeping our momentum going on all the acceleration stuff right now, just to be clear. Then we're going to pause when we're done with that and sort of slightly go to the side or to the back and do homework 3, just so you know, like the larger agenda and that the curriculum is happening, just it's happening, hopefully in a way that more organically responds to you. So you're not getting new homework until we do all that. Okay, so I'm going to flip, assuming this is all clear, we're going to start again. This is the sort of equation agenda that's going on right now. I think that especially in this class, the very top equation you saw for the first time, like I think you did see it. Wait, also you can hear me? No, obviously you can because Maria responded. Yeah, you can hear me. Okay. Oh, yeah. Oh. Okay. I'm going to look at the chat in 1 second. Let me just say for one, this top equation, I believe I established with you last class, last Wednesday. We're now going to start practicing it, but I think you've seen it. It's the definition of average acceleration. We're going to say a lot more about it. The equation after that, we haven't rigorously said yet. But we will. But I'm going to say right now, you may recognize from calculus, and I want you to start getting more and more used to this. If instantaneous velocity, which we established as a concept and an equation last class, if instantaneous velocity can be regarded as the first derivative of position back to time, if that's what velocity is, okay, and I'm going to go to the chat in a second. If velocity is the first derivative of position with respect to time, then instantaneous acceleration, i.e. acceleration without a bar on top, is the derivative of velocity. I mean, and we said that last time too. I'm going to say this more. I'm not saying this is the last time I'm ever going to say this, but just to kind of summarize, if velocity is the first derivative of position, then acceleration is the second derivative of position. That's what this second equation says. How do you use it is a little bit more complicated. It's not something that you algebraically plug and chug into the way the others, but it is a definition. It is, and it's there to distinguish. I'm going to move on in a second. I'm going to look in the chat, but please note that the top equation is a definition equation for acceleration with a bar over it. And the one after that is acceleration without a bar over it. Same thing that happened to us with velocities. We first define an average measurement, then we define an instantaneous measurement, because averages are easier to picture and easier to measure, but more approximate. And instantaneous quantities at a point, are harder to measure, harder to picture, harder to understand in a way, but more precise. So that's like the pattern that's going on here. And then the very last equation is our goal for either today or Wednesday. We haven't said anything about it yet. I'm not going to say anything about it yet, but that's our goal of where we're going. It's another different equation for average velocity. Notice again, it's V with a bar over it. If it seems like a contradiction to you or a redundancy, or if you're thinking at all like, wait, I thought we already had an equation for average velocity, we do. But notice the one we already have is a definition. It's a triple equal sign. It's always true. This one is a double equal sign. It's a discovery. It's a conditional. It's sometimes true. That's just an overall agenda of where we're going, or like summary of where we are. Fairly soon too, of course, I'll summarize I'll give you a sheet with all the equations we have so far. But I would argue that so far we basically have 5. All right, now I'm going to look at. So I'm going to go on. I'm going to start walking through homework 4. Like from top to bottom, walking through in a moment. But first, I do see there's things in the chat, so hang on, bear with me. Okay. Right. Okay. Homework 4 is not hard. Yeah. So I'm looking at Shawnee's thing. If you've been focused on homework 4 lately, and maybe even a little bit anxious about or something nervous about, then you're totally in the right place, and that's why I'm going to focus on it now. And if if you've been focusing on that, that's why I'm going to focus on it. And if you've been finding it harder going back and forth, I'm here for you. That's what I mean. No joke. Like, it is hard. It is a leap. We're getting into physics now, for real. So that's what we're about to do. So don't, if you've been doing it at all, if you've been thinking about it at all, any of you, then you're in the right place at the right time. Like, I'm not kidding. And if you've been struggling with it slightly, welcome to the club. Like, you are not crazy. You are not alone. You are not irresponsible. That is what we're. But now, oh my audio cuts. Okay, okay. Oh, and you can get the textbook. We can talk about that too in private. I'm happy to talk about the textbook. I mean, I have lots of things. I don't want to discourage anybody from getting a textbook. And if anybody, and I also don't want, I can't like, wait. Also, I'm hearing in the chat that my audio is cutting in and out, which I believe. Hang on a second. Let me do something about that before. Let me try. Thank you for telling me. Hold on. My new thing is I'm using AirPods for the microphone because my computer microphone is dead. Tell me, wait a minute. I think I'm totally out. I think, wait. Like, can you guys hear me at all right now? Thank you. And is it seem you can? All right, thank you, Shy. And is it okay? Thank you, Alex. And is it slightly better than before? Well, you'll tell me. I think it might be more, okay. Okay, cool. And it is better. Okay, okay, cool. So hopefully, but let me know again. I like this feedback. Thank you. And I'm gonna get rolling. But just on the Shawnee thing, as far as textbooks, I know I'm very weird about textbooks. Like, bottom line is, I don't assign them anymore. I just literally don't assign them anymore because I don't want to spend your. It's kind of like this. I don't want to spend your money. I don't use them enough to spend your money on it. I do. I do like them enough that people that can get free copies or old copies or things like that, I think it's worth it. But it's not really responsible for me as a professor to go in public and start encouraging you to, like, get books without paying for them. If anybody is, I definitely know the book that I would recommend. And I think it's still in our syllabus. I know the book that I would recommend. And if anybody ever wants to talk to me privately about what book I would recommend, happy to do that. And like Shawnee's saying, it's great if you get it. And if you ever come to private, say like, and you come to me privately, say, so where are we in the textbook right now? Of course, I'm happy to help you. I don't, I think it's a really good resource, our textbook. But I think at this point, with the internet and everything and all the millions of different resources that are out there that are specific to each one of your needs as a student, I think it's just, I don't want to limit to one. But if you got one, great. And I can help you how to use it. Okay. So I'm going to go on now. I think, so hopefully, oh, cool. Thank you. I appreciate that. Oh, cool. Oh, and Sean, okay, great. I see. Great, good. But yes, if you ever need me to be more specific about like where we are in the book, I'm happy to do that. Okay. All right. So let's get rolling. No, I appreciate all this feedback. I'm going to turn the page. I'm going to just bear with me for a second. I'm going to bring up my sheet. Oh, section 2. Well, there she goes. All right, Shawnee, she's all over it. All right, awesome. All right. But I'm going to go to the actual sheet. Just bear with me. We're coming. Okay. Right. And I'm also going to say, oh, I'm sorry. I'm also going to say that I'm going to flip back and forth here. I hope you're getting used to this too. Like in the interest of time and efficiency, on the big sort of main problems, I'll do the 5-step method explicitly, but on some problems or fast exercises, I'm just going to give answers. And I hope you understand that. So sometimes I'm doing exactly what I would accept as, make this clear. So in other words, just providing answers. The reason I'm saying that explicitly is then I don't want, like when we get to an exam, if someone does something like this and just writes answers and then said, for problems that are similar and then says, well, this is what you did. Like, no. Okay, I think you understand that. On that, to that end, there's one other thing I was going to say before we even get started. Side note, which could be controversial, but I have to say it before I forget it because I'm getting old. Homework two, right? I went over the hard, long problem of on the video. I went on homework two. I'm saying now, this is a sidebar. On homework two, on the video, I went over this long problem called hill figure, where you went up at 40 miles an hour, you went down at 60 miles an hour, and the average speed for the whole thing was not 50. The big punchline of the whole thing was that going up at 40, coming down at 60, the average speed was not 50. The average speed was 48. Again, I'm encouraging that everybody watch that video and understands it, blah, blah, blah. But therefore, once you understand that, once you understand that or know what questions you need to ask me about it, then I want to say, then you're in a position where you could do the very last problem on that homework. Even if you got it wrong the first time, once you understand the second to last problem, you're in a position where you can use the same logic to do the Little Red Riding Hood problem. I forget what Grandma Grimm it's called, where you go out, you come in, and different types of information are given and a different type of ultimate answer is asked for, but it literally is the same problem, just it's practice of the same idea, but with the information scrambled around a bit. And if you do that, and you should do it for practice, like something like this often is on the first exam, you should go back and look at that last one for practice, and you will find, if you do it correctly, that the answer is one step slightly harder than the answer from the second last. The answer is infinity, okay? Or in English, the answer is there. No matter how fast she goes, she cannot accomplish the task. She cannot accomplish the given task of the last problem by going at any finite speed. I am just saying that right now, and I'm going to move on. But again, just so that you know the correct answers or whatever, make a note of that, please. If you got it right, pat yourself on the back. Really, really, really. If you didn't get it right yet and you're still working on it, like note it. And if you're still confused, text me or email me. I'm really serious, but that's like a litmus test if you understood the video from the earlier part of homework two. Okay, I'm just getting that out of the way. Now I'm going to move on to homework four. The first question. Oh, sidebar question about exams. Yeah, okay. So Maria, that's a legitimate question. And and I'm trying to good question. Once we start talking about exams, we're going to say a lot about exams, and I'll answer a lot of questions like that. My quick answer is generally with exams, what we end up doing is going over the areas where there was the most common difficulty. I don't walk through the whole exam like step by step after we take it, but generally an area of difficulty we do. Often an area of difficulty, after going over it, I'll reassign it or something for extra credit. That's not a promise, but often that happens. And then also, just to answer Maria's question further, what we really do, to be honest, is not to be honest, but yes, to be honest, we always get a practice exam before the exam, and the practice exam looks very similar to the actual exam, very similar. And it's meant to reduce surprises. And the practice exam, and it's meant for practice. The practice exam never counts. It never counts for points, but it is like a rough draft of the actual exam. And the reason I'm bringing that up is that with the practice exam, in various different ways, we go over the practice exam before you take the actual exam. Like some of that is in lab often, and some of it is here, and some of it's in videos, blah, blah, blah. But so the real semi-long answer to Maria's question is, we actually spend more time going over an exam before it, sort of, than after it. But after it, we will. So that's the honest answer. We don't walk through it afterwards, but we often will examine and walk through areas of common difficulty. So I don't know if that's like the answer you want, but I think that is the answer. Oh, cool. Okay, great. Thank you, Maria. Okay, awesome. So now I'm back to homework 4. So the first one. Okay, this is meant to be a quick review. This is not meant to be, I'm just going to do the answers here, like I said. But I did get some questions from some people over the weekend about this, which I do appreciate. So I'm going to say right away, yeah, we're supposed to draw a picture. I want to make sure, I'm not going to draw the picture right now again, but you are supposed to draw a picture and stuff, and you're supposed to, put north somewhere and south somewhere. And ideally, well, I am going to draw a picture. Okay, because I got enough questions about this. Say this is Berlin and say this is Rome. So when we draw pictures, when we do step 1 DFP, one of the main purposes of step 1 DFP is to use your pictures labels as means of defining terms, constants, variables, and directions that are going to be used in your math, whether the problem is simple or the problem is hard. You're especially going to see when we go over homework 3 that using your picture to define a coordinate system, to define what we mean by positive and what we mean by negative on each axis of space that we're dealing with. And right now, we're only dealing with one axis of space. That's a crucial part of the pictures. So I would recommend a picture like this where north is clear and south is clear, and where we maybe then go the extra step to ourselves impose a positive and negative designation on north and south. Doesn't have to be the one I chose. You could make south positive, but you should get in the habit of making a choice as to what you're going to numerically call positive and what you're going to call negative. Should. Now, because the real thing that the review is just trying to get at, it's not like hard math or anything like that. And some of the people who wrote me were like, they were almost confused because it like almost seemed too easy to them, or they thought it was a trick, or like they didn't like the fact that their answers were so similar. But it's not a trick. It's just trying to set up that like we want to always know from now on that displacement cares about direction, distance does not. Average velocity cares about direction, average speed does not. So honestly, like, just to be sort of quick, so that, and I meant to do that picture in black. I'm sorry. I'm trying to do my answers in black. You can remind me in chat if you want. Like, for what it's worth, that's what I'm trying. I try to do the questions in blue and the notations in red and the answers in black, but I always forget. But you can remind me in the chat. But so for the answers for like question A, total distance, the total distance is, this is my label. Distance is 700 miles. I mean, that's the answer. But for question B, honestly, the way the question is phrased, it asks for displacement, right? So you might even be a little bit more mathematical notation about it if you like. The displacement, and I'm skipping steps here. You notice I didn't write down step number 2 really, and I didn't really write down step number 3. I'm just cutting to the chase. But I think the displacement, if she flew straight from Berlin to Rome, which is from north to south, I would say that the displacement is negative 700 miles. In my notation, because I made south negative, I would say that the displacement is negative 700. Now, 2 things about this, because again, like people wrote me about this, so I just want to be clear. It's not, we got to get, let me just be clear. Did your answer, but that is my answer though. Sorry. My answer is that displacement is negative 700 miles. Did your answer have to be negative 700? No, it did not, because you might have done a different coordinate system or a different way of labeling direction. You might have labeled north negative and south positive, in which case you might have said that your displacement is positive 700 miles. That's fine, as long as it matched something that you made clear in your diagram. Or maybe you still don't like quite the positive negative thing, or the problem never literally said anything about positive and negative. So maybe you left it in English. That's fine, although we want to get in the habit of turning these things into math. But see, even if you left it in English, if you did draw a proper diagram and you labeled Rome as south and you labeled Berlin as north, then still if it's asking for displacement, I'm not saying this angrily, I'm almost happy because people ask me about it. If you're saying displacement, it's got to include a direction. So you at least have to include the word south somehow. You see what I mean? Like, and then you could call that positive or negative or neither, but somehow the direction has to be in your answer for cube. And that's why it says that your answers are slightly different. Okay. And then, so question C, and again, I'm talking fast because I am, but that doesn't mean you can't stop me. So then the average speed, I would say the average speed is 700 miles per whatever, 4 hours. Right. So that's like 175 miles per hour. Okay, so that's the answer to that one. And then I'm turning the page. You can tell me to turn back at any time. I'm going to question D. What's the average? Right. Okay. What's the average velocity for this? So average velocity. So now I'm sort of using the more mathematical or more symbolic looking thing. The average velocity is displacement over time. So I think the displacement is negative 700 miles, and I think the time is 4 hours. So I think the average velocity is 175 miles per hour. Okay, and so is negative. I'm sorry, is negative. So those are my 4 answers. Now, again, those are answers. I didn't write step 3. I didn't really write out step 2 or step 4. Please note that. So if this were an exam, you'd need to do more than this, but I'm just highlighting what I think the issues were that I heard about over the weekend. But I think those are the answers. I'm going to look in the chat. Hold on.
Professor.
Oh, sorry. Yes, yes.
Okay, so when I did this question, I got all the same answers, but like my negative and positive are different based on the way that I drew my sketch. Is that okay?
That's what I'm saying. As long as, and this is the importance of a sketch, if you gave a sketch where you made clear, for example, in your sketch, you made it clear that south was positive and north was negative, and so then therefore your answers are different, that's great. If your answers are different from mine, but they're consistent with your sketch, then doubly awesome. Like, yes, and that's the whole importance of the sketch. So yes, as long as your sketch made it clear what you were doing and then you're consistent with it, 100% yes. So awesome. Cool. Okay. So, and again, to everybody who's still like with me or whatever, honestly, every time I say something like, as long as your answers are consistent with your sketch, or as long as your answers are consistent with your choice of coordinate axes, or your choice of perspective, or your choice of reference frame, that's really what homework 3 is all trying to get at. And we're going to go back to it. But just so that you all know, none of this is busy work. All this, we're trying to make one big, like, logical system that all actually makes sense, I believe, in the end. So homework 3 is all about getting us used to this idea that we have choices to make in physics. We really do, and we really can make those choices. But the flip side is we actually really have to make those choices and then stick with them. So anyway, but yes, so good, Shawnee, absolutely. And good question 20 minutes ago, Maria, and good question over the weekend, those people who asked who I'm not going to name by name. Oh, Paulina, question. Yeah. Oh, wow. Awesome. Oh, I love how you did that. Okay. Yeah. Paulina, please. Yes.
I just wanted to ask, in general, would north be considered positive and south would be considered like negative?
Great question also. And the way you phrased it is perfect. In general, when all everything else is equal, if there's no other considerations, yes, the custom is that on that axis, people tend to make north positive. And then on the other axis, or like on another axis, people tend to make east positive and west negative. Physicists tend to, yes. And there are some advantages to doing that, yes, but it's really perfect the way you phrase that. Like, in general, yes, when in doubt, if you've got no other reason to do anything else, that's a good way to go. But there are a lot of circumstances where it makes sense to go against that, where physicists will go against that. And that's why we're just always clear right up at the front of what we're doing. But yes, that is the general, and just like also on a number line, we tend to make right positive and left negative. But so yes, but you definitely can go against that, and often it's smart to go against it as long as you clearly and consciously are going against it. But yes, great question. Wow, people are like asking a lot of questions. And also, I love that electronic hand because I wouldn't, and the sound that it made, that's new. That helped because I couldn't actually see. Okay, anyway, so now we're gonna go on, but yeah, keep the questions coming for sure. Okay, now we're getting into something. All right. Question 2, now I should be in blue. 2, instantaneous. So now we're gonna get into the whole thing that we got into last class, only we're going into it now from like a back door. Because again, remember this homework sheet was assigned on purpose, like before we even like had the last class. Now that's not an accident. So something about this question, I'll remind you the question, but something about this next question is assuming that we could somehow figure it out even without that last class or even without a textbook. Like it is assuming that if we like think hard enough about anything we already know, somehow we're gonna like work our way to this concept. So what it says, just to read, I mean, hopefully you're looking yourselves on your side, but question 2 says like, no, we have not yet established a method for computing instantaneous velocity, but the key point right now is that we believe it exists and can be computed. Okay, so we're believing that there's a thing called velocity at an instant, instantaneous velocity, which just means just what the words say, instantaneous velocity, velocity at an instant, like we said last week, like the thing that the police officer presumably cares about when the police officer pulls you over and says, do you know how fast you were just going? Right? Again, and I know they always make this sort of joke, but it's not a joke. Like they do not want you to do a computation, and they're not doing a computation. They're not saying we've been following you for 2 hours and you've covered this much distance in those 2 hours. So in general, or on average, you must be going very fast, right? Like that's not what they're getting at, because for 1,000 reasons. They're saying right now, at this moment, you are by school with little children and you went super fast. I don't care if you parked at a rest station 15 minutes before that and you parked at the rest station for so long that you averaged out your general average speed for the day. Like we don't care what you're doing on average for the day or for the hour. You just passed the school going dangerously fast. We're pulling, right? That's what instantaneous velocity is about, is how fast you're going right now. Now, no one's saying we know how to compute it yet. This stage in the homework sheet, but it says in the homework sheet, sometimes you can compute it without thinking too hard, as long as you believe as long as you believe in it, which sounds very emotional, but it's true. And so here's the example. So here's the example is a car. Let me, I'll just sketch it quickly. It says, okay, so example. Constant velocity for 30 minutes. Okay, so t equals 30 minutes. And for that 30 minutes, its velocity is constant. So how do I write that symbolically? I would say this, and you may want to make a note of this. I think I've done this before, but I'm going to keep doing it. If I write v equals v naught, right, that is mathematical terminology. That is symbolism for velocity remains constant, right? Because it's saying mathematically whatever the velocity was right at the first moment is what it is at every moment. That's what that means, right? So we got that fact. And then it says, another fact that we're told is during the 30 minutes, this displacement is 40 miles. Say this. It's now to what I'm going to make a decision now that I've sort of never done before, not exactly done before. And it totally relates to what someone just asked me. Thank you for that link. We got to be careful about links like that because this is sort of public and I'm sort of, all right. Thank you. No, I do appreciate what Shawnee just put in the chat. Let's just be a little bit careful, things like that, because if it's not legal, I'm not sure that like I really want to go on public record endorsing it, but okay. But no, but thank you, Shawnee. And I guess the chat doesn't get put. All right, but thank you. But also I want to say back to the question that I think it was Paulina asked about like, do we generally make North? And correct me if it wasn't Paulina, tell me in the chat privately, because I want to give credit where credit is due. But I believe it was Paulina who asked, like, do we generally make North positive and stuff like that? And I said yes. Similarly, I want to make a note right now. What I'm doing right here, because I may be otherwise confusing people. I'm right now, in fact, yeah, I'm right now setting up a coordinate system. I could draw a diagram. I should draw a diagram. Situation where we're told that the time is 30 minutes, the displacement is 40 miles, and we're told that the velocity is constant. I'm now saying here specifically, let the place where this car began, let that be known as place 0. That's a decision I'm making. That's like part of labeling my coordinate system, right? I'm calling everything this way positive. I'm going to call everything to the other way negative, and I'm calling the place where the car started as 0. Now, I'm doing this right now, as usual, at a place where I don't think it's that big of a deal. I think even if you didn't do that, you still could get this question right. But you notice that I'm using over and over again, I'm using this equation up here, average velocity equals displacement over time. Displacement is current position or final position minus initial position, right? I want to make it clear to you guys that initial position isn't necessarily always 0. It wasn't 0 in homework 1. Things can start at a place that is not called 0, as did occur in homework 1. But going back to Paulina's question, but if we have no reason to believe otherwise, if we're not given any information that says the very first place you start is at like the 4th meter mark or whatever, then we should, as physicists, make choices that make our life as easy as possible. So just like it makes it easier to call North positive in a lot of circumstances, it also makes it easier and more convenient to call wherever you're starting 0, as long as you can get away with that, because then there's less to subtract and less to do in the equations. So I'm going to get in the habit right now, when I can, I'm going to say, let the initial position of this situation be called 0. Therefore, if and when I go to plug into that equation up at the top of the board, this equation, that equation there, I'll be able to just plug in a 0 for that x naught. And I want to say right now, I may have lost some people a couple of times in going over other things. A lot of times I write that equation and then I just put a number in the numerator, like I did like 175 or 700 I put in the last problem, because I'm already in my mind assuming that x naught is 0. That is a thing that I can do as long as I can, as long as I make that choice and nothing else contradicts it. We can often choose to call x naught 0, but we do have to make the choice. It's not automatically. All right, that long story, but so I'm just doing that here. Okay, so now the question is, going back to the question, it's, right. Well, hold on. Yeah. That is definitely the textbook. No, I do appreciate it, Shawnee. That is definitely the textbook that I'm recommending. I'm just, okay, as long as that's a legal place to get it. All right, I won't, okay, fine. I retract anything. Yes, that is, let me confirm. She's right. That is the textbook that I do recommend. That is the best textbook for this class. That is absolutely true. Since I don't know all right, I'm going to keep talking. Yes, and I don't mean to argue with anybody. So the sheet says now, given those facts, the question is, the step 2. Question is, at E equals 18. or whatever it says, at the 18th minute, 42nd second, what is the instantaneous velocity v, right? That's what it asks for this question. Now, I want to be careful about this. In a way, it's totally gettable by everybody. It is gettable. The right answer is gettable for the right reasons. The right answer is also gettable for the wrong reasons here. So let me be very careful. We have a car that's going 40 miles in 30 minutes, right? So that much we know. So if I were doing like step 3, GDP, I'm going to write down some kind of principle or law or definition that I know in order to get something. The one that I'm most reliant on right now in this class, the one that I know the most comfortably and is always true, is this definition of average velocity, right? I know the definition of average velocity, so I write it. It's true. So I write it down. Now, note, that's not what the question's asking. The question is asking for instantaneous velocity. This is an example of a physics question now. Like, I'm writing down something that is true, that I know is true, that I'm hoping that I can use. Okay, yes, and thank you, Katie. Awesome. Thank you, Katie, for thanking Sean. Okay, I'm writing something that please bear with me on this. Even if you got the right answer to this question, or whether you thought it was easy or hard, notice the 5-step method in action here. I am writing down something that is true, that is definitely true, and probably going to help me. But it is a step. I'm writing it down because I know it's true and I think I'm going to use it. It's not what the question's asking. It doesn't land me at the end of the question yet. Like, the question is asking about V without a bar on it. It's asking for instantaneous V. However, I'm writing something down first that I know I can rely on and will hopefully get me to where I'm going, right? So I'm writing down V with a bar, average velocity. So again, you notice it, in blue, it's asking for V without a bar. In black, I'm writing down what V with a bar is, okay? And okay, and then I'm going to step 4. Well, go to step 4. Step 4, like, I'll start plugging in or whatever. Like here, X minus X naught, we know is 40 miles, okay? And we know the T is 30 minutes. Maybe to be fair, let me call that like hour, just so I can sort of convert this into numbers that are sort of reasonable, or more common. Like, well, you don't have to do that, but I'm doing that. So here, V bar equals like 45 hour, which is 80 miles per hour. Okay, so I'm in step 4. I'm saying V bar equals 80 miles per hour. Now, please listen careful, or please let's be careful about this. You might think that's the answer. Maybe it is, but maybe it isn't. Right now, what I'm telling you, I'm not going to do, I'm not going to circle that and say step 5, FAC, we're done. It's 80 miles. What I have right now is that the average velocity for the whole journey is 80 miles per hour. That in itself does not mean, that fact by itself does not mean that the car is going exactly 80 miles per hour at any given moment, right? It's an average. It means on average it was going that fast. In general, what averages mean is sometimes you can go slower and sometimes faster, but altogether you're doing the equivalent of a certain number. That is the average. It's not what the question's asking. I'm just going to write it down. So we know, so the average is 80 miles per hour. But the question also states equals V naught, right? The question says that at any given moment, what we're doing is exactly the same as what we were doing at the beginning, which means that at any given moment, what we're doing must be the same as the average. This is important. Again, I'm both saying that this question's easier than it sounds, and I'm saying it's harder than it sounds. What I'm saying is, well, so I'm saying thus. Okay, I'm going to go back to, I promise, I'm going to go to the next page just for a second, just so I can wrap this up, and then I'm going to go back. I'm saying, what I am saying, I will turn back in 1 second. I know somebody needs that, but I'm saying, just to wrap this up, step 5. Yes, if you believe that the answer to this question is 80 miles, you are correct, or at whatever that was, at t equals, whatever it was, at t equals blah, 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 blah. Yes, the answer is v equals 80 miles per hour. That is the answer. Some people didn't get it right because the question seems too intimidating. Some people got it right, but sort of by accident, sort of by skipping steps. That is the answer. Now I'm going to turn back the page just so you saw everything I just wrote. But what I'm trying to drum in here, I'm saying, I want to make sure before we go any further, the big lesson, the big takeaway from the last class is that as concepts, instantaneous velocity and average velocity do not mean the same thing. They are not the same concept. As far as triple equal signs are concerned, v without a bar on it is not the same thing as v with a bar. And generally, I love that Paulina used that word. I don't know why, but it's like a really good word in physics. I do know why, but it's not worth going into. Generally, the numerical answer to an instantaneous velocity is not the same as the numerical answer to an average velocity. Generally, computing or calculating instantaneous velocity will take some kind of interesting work, maybe calculus. What this weird problem is partly trying to show that they're not the same concept. It's trying to sort of introduce you to the concept of instantaneous velocity, but it's also at the same trying to say the way we get instantaneous velocity, the way we ever compute instantaneous velocity, velocity at a moment, velocity at a snapshot, is that we always look at the snapshot in the context of the larger movie from which we're taking it, like during which we're examining it. What we're saying is even when you do calculus, what calculus really is a method of zooming in from a larger context into a tiny context. Calculus is a way of zooming in from context to a point and saying, even though nothing should be happening at a point by itself, even though no motion should be happening in a isolated photograph, if the photograph is part of a context of a larger movie, then from context, from zooming in, we can see what that photograph or that frame or whatever is capturing, or that, in other words, there's no slope of a dot. A dot does not have a slope, but we can still, using calculus, talk about the slope of a curve at a dot. That's what we're always doing when we talk about instantaneous velocity. We're talking about a rate of change of a larger phenomenon at some slice of that phenomenon, right? So why am I yelling? Because I'm always yelling. Why am I like getting excited about this? Because here in this question, out of nowhere, even though we don't have any formulas, we haven't like reviewed, we hadn't even reviewed limits or derivatives or anything here, it's all of a sudden just saying, hey, you got this car, it's going down the highway. What's its instantaneous velocity right now? And in some way, that should be a very unfair question. I don't have to know like what its instantaneous velocity is right now. Well, did you give me any facts? Well, the facts they gave us were in effect the average velocity for the whole thing. So then we're like, all right, that's the average velocity for the whole thing. I mean, we got that here on page 5. Like we got the average velocity for the whole thing. And then some people, and that's a good way to start. And if you have confidence in yourself, the ideal thing is you start with that, and yet no, you're not done yet. Some people started, got the average, and were like, okay, that's the answer. Well, it's not that that's accidentally it's not that that's automatically the answer. That 80 is the average for the whole thing. And just because it's the average for the whole thing doesn't mean it's the instantaneous velocity at any point. But if someone gave us that extra crucial fact and said, oh yeah, but by the way, not only is that the average for the whole thing, but I'm going to just tell you this extra fact, which is this car never changed its speed at all, its velocity at all. It was always going the same velocity. Then we can say, oh, so this is literally like this. And I'm going to move on right after this, but I just want to drum this in. And what am I drumming in? I'm drumming in that how we get instantaneous velocity at a moment, ultimately, one way or another, is we get it from context. Some contexts are simpler to see than others. If the context gets complicated enough, we use calculus, but we're always using the context. The context here is that someone basically walked up to you and said, hey, I'm going to tell you 2 facts. One, I'm going to tell you 2 facts. You took a whole bunch of exams in this course, a whole bunch of exams. Here's the 2 facts. One, your average was a 94. And fact number 2, you always got the same score on every single test. Fact number 1 is your average was 94. Fact number 2 is you got the exact same score on every single test. So here's the question. What did you get? In fact, I'm going to ask you all right now in the chat, just to make sure, since I've been yelling about this for so long, just make sure I'm clear. I'm just going to wait for a couple people to reply to the chat. But here's the question I'm asking in the chat. I mean, I'm asking you of the chat. You can reply publicly or privately. I don't care. I'm saying you take a whole bunch of exams in a class. Your average is a 94, and you get the exact same score on every single exam. So what did you get on the 3rd exam? I'll repeat. And as soon as I get a couple answers in the chat, I'm going to move on. But I'll repeat. Your average in a class is, you take a whole bunch of exams in a class. Your average is a 94. You get the exact same score on every exam. What? Oh, there is stuff in the chat. Great. Oh, you're so with me. Wow. Like 7, awesome. Like 8 of you just responded simultaneously. So you get it. So I'm moving on. That's awesome. Yay. Good. Okay. But that just proves, if nothing else, that proves we can get hard things like instantaneous velocity without weird equations. We just eventually build the equations as the situations get harder and harder. But okay, I'm going to the next question now. Great. Okay, so now we're talking about average. Oh yeah, and so it refers to the textbook there. That's ironic. No wonder the whole Shawnee discussion. Okay, well yeah, there you go. That is still the good textbook. Okay, and you know, that textbook was, or one of the authors was the professor Graff. If you've ever had Dr. Graff in the math department at John Jay, if you've ever had Dr. Graff, he went to the school where this book was written, and he had one of these authors as a professor, which is very nice. Okay, so number 3. Now I'm going to try to do this a little faster. Again, I'm just going to do answers for a little while because I'm talking too much as usual. So this is A. 60 miles. Not doing the steps, I'm just doing the answer. Expressed in miles per hour per minute, what's the average acceleration of the Toyota? Okay, the GDP is acceleration. Average acceleration. Okay, it wrote it as like deltas in there on the sheet. I'm writing it here this way. It means the exact same thing. We've discussed this before. Like because I could say it like this. It's just like the other equation. It's change in instantaneous velocity over change in time, but T naught is always equal to 0. So I can write it like that, right? Okay, same thing. So this question, so average, sorry, did I put it? Sorry, average acceleration. acceleration equals change in velocity per time. Please note, again, I'm going to keep saying this. Notice a list of equations, but notice this equation has the exact same form as V bar equals X minus X naught over T. The exact same form. Notice on the left side is a bar. On the right side is not bars, not a coincidence. It always works that way. But okay, so I'm going to plug in. Facts. Now notice this is sort of intentional. In question A, it wants the average acceleration of the Toyota expressed in miles per hour per minute. You might think that's sort of awkward. You might find that surprising because it doesn't sound like standard science or whatever, but it is the units that these facts were given in. So it's actually making, but it is legitimate. It is 100% legitimate. It's not common. It's not what physicists would generally do. Thank you, Paulina. But it is perfectly reasonable, and it's convenient because these are the units that we were given here. So in other words, what I'm saying is the answer to question A is average acceleration equals 30 miles per hour per minute. This is an answer. Now let's pause for a second. There was no hard math to do there. It was intentionally set up. The units were intentionally set up so that number one, you didn't have to do crazy unit conversion. Number two, the units were set up so that they are commonly recognized units. Like they might not be general for physicists, but they are general for life, right? Like if you ever, I mean, I think I asked this class last, I mean, a lot of you in this class drive. I don't remember if a lot of you do drive. And you know that like on the highway or the LIE or whatever, miles per hour is the way we talk about things in America, right? And minutes are the way we talk about time in America. So these are like reasonable numbers that we can relate to. A Toyota that takes 2 minutes to accelerate up to 60 miles per hour is a pretty weak Toyota. But notice in the end of the day, the answer we're getting here is a legitimate answer for acceleration because what it has is units of, how can I say this? Units. Velocity is change in where you are per time. Velocity is change in position per time. Velocity is measured in space per time, such as in science, meters per second, or in America, miles per hour, right? Like, I'm not being sarcastic, right? It's like velocity is space per time. Now, acceleration is change in velocity per time. So it's change in that per time. Remember, acceleration is like speed of the speed. It's not speed, it's speed of the speed. It's not rate of change of position, it's rate of change, right? It's a direct analogy, but it's not a direct equivalent. Again, this whole relationship that we're going in levels of change here is exactly what physics is really about in the end, is levels of change. If you can get that each time we go up a level, we go up a level, then you really understand something. So acceleration, like I'm gonna dwell on this a tiny bit more. Like car commercials. I mean, I don't see that. I assume car commercials still talk about things like the new Toyota, blah, blah, blah. goes 0 to 60 in, like, they don't advertise a car by saying the new car blah, 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 goes 0 to 60. They don't say that. All cars go 0 to 60. Like, that's not interesting. Any car that exists can go from 0 miles per hour to 60 miles per hour. That doesn't say anything about the car. What they say on car commercials or whatever is that this car can go from a certain velocity to another certain velocity in a certain amount of time. Like, that's their big advertisement, that the shorter amount of time it takes to get from one velocity to another, that means the more acceleration it has. It means the more responsive the gas pedal is. Like, the more it changes, it like jumps the way you want it to when you want it to, right? So acceleration is measured in units of space per time. And there's no rule. This one's trying to say this exercise is trying to say there's no rule that the time units have to match. Ultimately, do we like them to match in science because it makes it more consistent and easier to deal with other numbers? Yes. So that's why we go to question B in a moment. But like, I think this is easier to relate to as a human being. This car has an acceleration rate of 30 miles per hour per minute, meaning every minute, if this kept up like this constantly forever, every minute the speedometer needle would move to another new 30 miles per hour rate. It's like at 0, it's going 0. At 1 minute, it's going 30 miles per hour of velocity. At 2 minutes, it's going 60 miles per hour of velocity, etc. Last thing I'm going to say, but I hope you understand. So this answer is correct, and it's fine. I think it's relatable, even though it's not metric. But please also understand, this answer doesn't say anything about distance. Nobody's asking in this question how far the Toyota gets. Just as a warning, or for the questions that are to come, if I asked you how far this Toyota gets in 3 minutes, the answer is not 90. I'm just saying that. If I say how far does the Toyota get in 3 minutes, it's not 90. Why did I even get 90? 90 is 30 times 3, right? What does 30 times 3, 90 mean? It means in 3 minutes, this car will be going at an instantaneous velocity of 90 miles per hour. That's what this pattern means, right? And in 4 minutes, it will be going 120 miles per hour, et cetera, et cetera. That's what this number means. That's what acceleration means. Okay, so then we go to the next question, question B. You want to say, and there it just asks you to do the unit conversion, because yeah, I mean, and then we're still in miles rather than meters. We could convert it all the way to meters if we wanted, but it now asks you to do the unit conversion. And the way to do this, so if we said that A equals once, I know we're running out of time. Let me look at the rest of the questions. I know we have to get to the next questions for real. Actually, I don't want to dwell on this. I'm dwelling a little bit. I'm going to say what to do, and I'm going to move on. And if you have questions, ask me. Like, you might want to remind me in the chat. Oh, be a 4. I feel like if I remember, it used to be a 4 somehow, but maybe it's the answer. I may be off by 1 decimal place. Tell me if you got -4, let me know. I feel like I used to always get -4 in the back. I'm just forgetting. But... So I think that's the answer. 2 quick things about that. So you want to have sidebar conversations about how to do the unit conversions. I know that's still a concern for a lot of people. It can get confusing, especially if the units are in the denominator. But one quick summary is like, if I know already how fast this thing is going in hours. All right, so hold on, let me check again for a second. Did I forget a fact? 10 to the -4 is familiar, but where am I getting? All right, hold on 1 second. You got the same as, okay, so, and it's 1.33, not 8, because I feel like I remember the 8, but all right, did you do, okay, we'll dwell on this for a second. And obviously, by the way, again, folks, I'm gonna just remind you, you don't have new homework yet. We're gonna keep going just with this on Wednesday, because I know the time is gonna run out soon. But I don't want to leave you with something wrong or a mistake, but you got to say, and 2 people, 2 very active participants getting the same thing is definitely worth noting. So wait, oh, 30 was 30. No, it is 30. Oh, I know why. Oh, you're right. No, yeah. I did leave out. I'm sorry. I'm so sorry. I have to do it again. You're absolutely right. I see what I did. This, because this was in minutes. That's my bad. I miscopied. This thing was in minutes, wasn't it? Okay, right. The original fact was 30 miles per hour per minute, and I miscopied that as 30 miles per hour per second. So it's 30 miles per hour per minute. So you have to divide by 360, and then you have to divide by 60 again, because there are 60 seconds in 1 minute. Good point. These hours cancel, and you're left with seconds. Thank you both, Maria and Paulina and Alan and Alexa. Oh, great. Okay, awesome. So then also shows that I don't have to dwell on. Great, you guys are. So you got like this. You got like this, yes. Okay, great.
Yeah.
Awesome. And good. What a good class. Okay, thank you. And my apologies. And I am going to put up a portal for when people correct me, because I think it's like really good for everybody. I mean, if it happened all the time, we'd probably be a hate fest. But so then just 2 quick. So it seems like people, at least a lot of people in this room, are very good with unit conversion. So that's great. So just notice now, one of the reasons for this exercise is, yes, of course. And again, I'm going to just, and I do this, I'm going to keep referring to the Paulina point, the whole thing about general. It's not to make fun. It's definitely not. It's the opposite of making fun of Paulina. But it's also just because I'm now just putting the Paulina name on that concept. And I'll do that with other people's names to other concepts too. Okay, just to keep like this concept of what's generally accepted or not. Like, yes, of course, in physics, ultimately, what we tend to do is write accelerations in terms of miles per second squared, or even better, we tend to write accelerations meters per second squared. But that's what we tend to do. Here's miles per second squared. We tend to write in meters per second squared. The thing I want to emphasize to everybody about that, because I know people see that in high school, and it throws a lot of people off. Like, meters per second squared tends to be one of those moments in high school or early in physics where it just looks so weird and strange, and it looks like we're squaring time, or we're doing something so exotic that doesn't make sense, that it becomes one of those places where people start unconsciously melting down and deciding that physics is just like weird stuff that is mathy and doesn't have to do with the real world, and that we just like accept. But I'm here to say, no. It's like, it is about the real world, and it is not actually strange. It actually is logical when you break it down. So when we say meters per second squared, we're not actually saying anything about squaring time. What we're really saying is meters per second. We're really just saying the time units twice, but so they're both in the denominator, because it's really change in velocity per time. So it's change in space per time. So we have 2 units of time, and then we just abbreviate them by saying squared. Seconds times seconds, we just say a second squared. But it could have been miles per hour per minute is like what this whole illustration is trying to show. But it sounds like you guys get it anyway because you got the right answer, so that's great. And of course, the acceleration, once we're doing it in units of meters per second, miles per second squared, is a tiny, tiny acceleration, because how much could it actually speed up in every second if it was taking that many minutes to speed up? So, okay, so that's the answer to that. I know we have 4 minutes left. Let me just do a quick assessment of whether we can do one more thing. 4 minutes. I'm going to just bang through the answer. I promise. I'm not going to talk. I'm going to write down the answers for 4, and you'll see if you're right or wrong, and then we'll pick up with 5 tomorrow. And 6 is the really important thing. Whatever 6 we're going to dwell on tomorrow, Wednesday. But 4, I will just write down the answers right now so that we're. It's okay. All right, I'm going to choose the east. West is negative. This would be in the diagram. That's the point of a diagram. Okay. Page, I apologize. If you want me to go back, I'll do it like right when this is over, if that's okay. This, and we're going to end here. We have 1 minute. And we have like 30 seconds. I could turn back the page if you want. I'm looking in the chat. But okay. But those are the key answers to that. Like the bottom line of what this thing is trying to get at here, before we go any further, is that I just lost a sheet. The bottom line that it's getting at is that positive acceleration can mean speeding up if you're moving in a positive direction. It can also mean slowing down while moving in a negative direction, and vice versa with negative acceleration. In other words, acceleration is change in velocity. Velocity takes into account direction, takes into account pluses and minus sign. This is sort of why they were trying to warm you up with the whole Berlin-Rome thing at the beginning of the whole sheet. What we're ultimately trying to say is to accelerate negatively means to lose velocity, which means your velocity numbers are going down, that means either they could be coming decreasingly positive or increasingly negative. So you have to sort of think about that for a while. I mean, class is over, so just let that sink in. But that's what I just said is the answer to D of that question. So we'll quickly do 5 on Wednesday, and then we'll spend a little more time on 6, and then we'll do train of thought. So thank you. You've been very patient and very active and very smart as always. I really appreciate it. I'm here to answer questions, but have a nice day otherwise, and no new homework. Have a great day. Have a great. Thank you so much. Have a great day. Awesome.
Professor, I just had a question.
Awesome. Let me just turn off the recording for your sake once. I think for your sake.